Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
It's my pleasure today to introduce Mark Oskin, whose day job is no longer being an associate professor at UW. Mark has been doing a startup for a couple years now, and it's been a lot of fun sort of seeing Mark get the company going and seeing him discover what the real world looks like. And he's going to come and tell us about what they've built and the product they have and sort of why it works, which is great. Right. So, Mark.
Thanks, Jim. And thanks for inviting me out. And I know there's a lot of folks watching it over the net here around Microsoft, so welcome. Yes, Jim mentioned, my day job is a professor at the University of Washington, and I just want to acknowledge the other co-founders of the company, and as well as all the employees. It's been great fun working with this group. I'm here today to tell you about Jinx, and Jinx is a product that is almost to market. And what it does is it makes subtle and rare concurrency problems in your software not subtle and much more common. And so there's a lot of technology pieces that make that work. And so I have to kind of go through and give you a whirlwind tour of about 4 different pieces of technology that are built into it. So like every talk that I've given in the last 4 years, they all start with a slide that looks a lot like this. This is single-threaded performance dating back from 1987, although actually if you wanted to project back to 1950, it's about the same. X-axis is time, obviously. Y-axis is the log of single-threaded performance. So in reality, performance has gone like this up until June 2004, where it just flatlined. And the response to that, of course, is what we all know now is multicore. And what hardware vendors are giving us is ever more and more cores. Of course, that is all well and good for Intel and AMD, because they can keep selling them. But software developers have to somehow port their software over to using them. And I think I'm probably preaching to the choir here at Microsoft. We all know that this is an extremely difficult challenge to do. There's a lot of underlying problems that have to be solved in the software space if we're going to take advantage of chips like this that might be shipped in a few years. We're certainly at a big problem now. And if you think forward in 10 or 15 years, we have an even larger one. So what are those challenges? I think there's probably 3 broad classes of them. First of all, it's very difficult to architect real parallel software. We can teach students in the university about how to write, say, a parallel FIFO or some data structure that supports concurrent access. But when you talk about architecting million or 200 million line code bases, that's a completely different story. And there isn't really a good handle on how to do that and what the best industry practices are. It's also a pretty crude starting point. We don't produce students for you guys to hire that have this built-in knowledge, and there isn't this long experience. In the middle here, of course, is that once you've written the software, you have this huge challenge to actually get it right. The debugging of parallel software opens up a whole new set of errors that developers have to face, and there isn't a lot of experience, of course, with them. Things like data races, deadlocks, this phenomena where you run your program, and you get one answer, you run your program again, and you get a different answer, so-called Heisenbugs. And really what I would characterize as Stone Age tools. We're trying to write very complex concurrent software with tools that haven't changed significantly in their mental model of what features they can provide to you for the last 30 years. And that's a really difficult problem to solve. And then assuming you can actually write correct concurrent software, you have the next layer of challenge, which is how do you make it efficient? So algorithms that work well on 2 or 4 cores do not work well on 256 cores, and vice versa. So you have this next challenge of, now that I've actually written this thing, how do I make this thing efficient and scalable into the future? So what Petra has decided to do is really focus in this middle point. And the reason is, if you don't solve this challenge, which is being able to write correct parallel software, all bets are off. You have to be able to write software that works and ship software that works. Otherwise, people will not buy these cores, people will not buy the software, et cetera, et cetera. So this is kind of our first focus as a company, is helping people debug and write multi-threaded software. So our first product is what we call Jinx. And what Jinx is It's a tool that amplifies human effort in helping you find and understand concurrency errors. So what it is you install Jinx on your box, and by you I mean a developer or a quality assurance engineer. And then if you have a bug in your concurrent software, that bug is significantly more likely to appear. And if it's more likely to appear, you can then debug it. And moreover, when it does appear, there's characteristics about the machine that once it's happened that make it easier to understand the reasoning behind why that bug actually happened. So it has a set of benefits for you as a developer in QA, which is there's no false positives in this. When Jinx says, here's a bug, it is a bug. It's not like, we think this might be a bug because we've looked at these data accesses and they infer this possibility. It really is a bug. Jinx is able to actually look at your entire system. As you'll see later on in this talk, Jinx is a hypervisor that slips underneath your current box. So we're able to actually understand how all processes in your operating system are communicating and what the shared memory interaction is on those. It's language agnostic and it's synchronization primitive agnostic, so you don't have to sort of port your piece of code to some special primitives and then use those. A lot of customers out there in the marketplace write their own synchronization primitives. They write lock-free structures, etc. And so it works with all of those. And once we actually give you a bug, we actually give you the machine in a state that's more easily useful for you as a developer to understand why that bug has happened. And then overall, our real goal as a company is to kind of amplify human effort. If you should be able to install this product and reduce the amount of time that you have to spend finding and fixing concurrency problems. So those are what we think are kind of the benefits of what we're doing. So this is the high-level kind of 10,000-foot view of how Jinx works, which is I'm going to just imagine that time is going across here on the right, and I'm going to show you what a machine is actually doing as Jinx is installed and running on that box. So initially, the machine is running fairly normally, and then we sample the machine and freeze it and periodically explore several different ways at which forward progress could be made on the actual hardware. And then we pick one, and we replay that exact one onto the actual hardware that the user is experiencing, and we repeat this process. So we pick one, replay it onto reality, go forward in time, branch off, explore different realities, pick one, replay it on reality, branch off, et cetera, et cetera. Eventually what's going to happen is we will pick a way to make forward progress on a machine which leads to a bug, and then we replay that onto reality. Yes?
So when you do this parallel computation, trying out different features, are you doing that in parallel?
Yes, actually. Not only are we exploring different features, we're actually freezing the box, and then we're making several concurrent copies of the current state of the machine, and we're looking for many different ways it could make forward progress, and we're doing that in parallel again. So
there's no notion of going back in time. So it's not that you try one and then come back to the previous checkpoint.
So the way to think about it is that we take a checkpoint right here, and we explore this over and over and over again, looking for how to make forward progress here. And then we eventually pick one and then replay it onto reality. But there's no notion of, say, stopping here and then rolling all the way back to here and going forward. By the way, definitely feel free to interrupt me throughout this talk.
So just to clarify that, by the time you are at exploring the second red arrow,
right,
you had erased the source of the previous red arrow.
Right.
You have dropped it.
Exactly. Once we've committed this state to reality, to the real memory, to the real virtual machine, we throw all of that back and we allow the machine to make unchecked forward progress to here. And so there's no way for us to back up all the way to here. So we're really kind of backing up within these small windows and exploring the windows going forward from here, not all the way across. Other questions? Yeah.
Is the sampling just based on time or random sampling, or do you look for certain patterns which you say, you know, this would be a good time to export realities because I see something in particular going on?
A little both. So it's uniform random sampling to try and then at each point at which we have frozen the machine, we actually, before we go through this exhaustive process, we do kind of examine it and try and make some understanding of is this useful to debug. So for example, we ask you to tell us which applications you would like us to focus for testing. If those applications are not running, we don't go through the effort. That's the most obvious one, but there's others as well. Other questions? Great. All right, so just looking at this, there's a set of technologies that you actually need in order to make this work. So first of all, you need a way, if we have this bug, we would like to be able to describe the state of the machine in a useful way to the user. That's just one thing we would like to do. We need a way to kind of get in underneath the hood and intercept execution and take control of it over here. And we need a way to actually make forward progress inside of these what we call simulations of reality, such that we can deterministically replay a chosen reality onto the actual box. And so we need this is kind of a technology that we call deterministic multiprocessor execution. And then finally, kind of answering your question, you would like to be kind of judicious about when you do simulation. All right, so here's the outline for the rest of the talk. And really what I'm trying to do is give you a high-level view of the different technologies that Jinx implements in order for us to give you this product. And so first of all, it is a hypervisor. There is so that's one piece. It has the ability to execute the virtual machine of the hypervisor deterministically. So there's deterministic execution, which is another technology. There's a lot of kind of AI heuristics and control mechanisms that we use to try and find bugs and expose them. And then there's this way at which we present to you bugs, which we hope is kind of more useful than what we have now for presenting bugs. And that's something we call SmartStop. And then I'll finish off with a demo, which hopefully will work. All right, so one question you might have is, why did we go through the trouble of writing a hypervisor? And we actually wrote a hypervisor from scratch, so it was quite a lot of work. And so why would we go through that engineering exercise? The main reason is you have to implement this interception of execution somewhere. And there are several different places at which you could imagine doing it. You could do it in the compiler. You could do it as a runtime. You could do it in the operating system. And of course, you could do it one layer below the operating system in the hypervisor. And all these have different trade-offs. So if you wrote a compiler, the advantage there is you end up with a lot of very useful semantic knowledge of the application. And that's great. And we definitely studied that. The challenge is that in the marketplace, there's not one compiler that people use. There's 20 some odd compilers that people use. Several different variants of Microsoft's compilers. Some of them people are still using Microsoft compilers from the 90s. Some people are still using several different variants of GCC. So it's not like you can say, hey, I just want to implement a compiler, and then that's great. It's really an exercise in implementing 20 some odd different compilers. So that's just a logistical engineering challenge to do that. Kind of a logical place or an interesting place to do it would have been the operating system. But again, we wanted to build a Windows product, and so kind of deeply manipulating the structures and source code of the operating system for us was not an option. And so the next layer down was a hypervisor. And the nice thing about being down at that low layer is we have kind of understanding and insight to all of the machine state, what all of the processors are doing inside the entire operating system, which is kind of nifty. So it doesn't really matter what operating system we're using. It's very agnostic to that. I mean, currently the product is focused on Windows, but it's not hard to imagine slotting in a different OS there. All right, so we are not a normal hypervisor. If you think about VMware ESX or Xen, the way that those products are used is you first go through this process of installing a hypervisor or VMware or ESX or Xen. And then once you've installed that product, you install your operating system inside of it and you boot that. That was not the customer experience that we wanted. So what happens instead, and here's kind of the boot sequence on that, right? Normally what happens is you turn your machine on, you load the hypervisor, you load your guest OS, guest OS loads the apps. This is the reverse. It's what we call a thin hypervisor. You turn the machine on, you load the operating system, then you load Jinx, and Jinx actually squirrels its way underneath the current operating system and virtualizes it. And then you become a guest VM of our hypervisor. So we take a live running operating system, we virtualize it, and we go forward from there. Yeah?
You load the hypervisor as a driver.
Yes. So we are, from the user's perspective, we're a Windows driver. But then once you've installed us and you turn us on, your your operating system is actually now virtualized and under our control. So that's fun. How do you make one? So hypervisors are really primitive operating systems. They have threads, they have their own libraries, they have some very primitive device drivers. So we did all that. Answer to your question, yeah, you start out as driver code inside the Windows kernel. What's interesting about being a thin hypervisor instead of a normal one is that resources of the machine are actually cooperatively managed between the hypervisor and the guest operating system that it's virtualizing. So we actually communicate with Windows about what memory we would like, and then we take that memory and we stuff it inside of our own page tables and use it for our own purposes. So we're actually working cooperatively with the guest operating system. Then we execute a very, very carefully constructed sequence to start the VMX or the hardware layer VMX SVM virtual machine support. And then at that point, you're really in control of the whole machine. So you can do whatever you want. You can pass through various I/O. You can provide synthetic I/O. You can build soft TLBs, et cetera, et cetera. So at this point, you're basically like a normal hypervisor. Except you do have one caveat, which is that in a normal hypervisor, you can fake out and take away devices before you load the operating system. And we're the reverse. So really, since we're loaded after the fact, any devices that the operating system has talked to and configured and communicated with, we have to continue to support in some mechanism. Now, fortunately, it's not too hard. You mostly just pass all the device I/O directly down to the hardware and get out of the way. But on occasion, you don't.
I have a question.
Yeah.
Sounds very fascinating what you've done. I was wondering if you actually tested that you have implemented a real hypervisor by trying to load yet another operating system once you have done this.
We haven't done that.
Okay.
But I just imagine it would not be that hard, just knowing how we do it. Since we actually, you'll see later that we take, I guess you might think we do that. We actually take clones of the guest operating system and run copies of those, the clone looking for bugs inside of it. So although we're not loading a completely different guest image, we are taking a copy of the one that's there, running our tests looking for bugs inside that copy. So it's not quite an answer to your question, but related.
So one problem with regular hypervisor is that the hardware compatibility issues between real OSs and hypervisors. Like they're always playing catch up.
Yeah.
And so you are also part of the game. So you have to make sure that you support all the drivers, all the hardware.
It is a little bit of it's a little bit, but not as bad. So one of the things that's different about our hypervisor is we have no intention of trying to stack and run concurrently different guest operating systems at the same time. So we don't have synthetic devices. We don't have, for example, we don't have a synthetic network card that is being stacked on top of a real network card. So for the most part, our solution to all I/O devices is to simply get out of the way and pass the guest request directly down to hardware. Now, if we wanted to synthesize them, so for example, suppose we wanted to do, in answer to his question, Shaz's question, run Linux after the fact inside of Microsoft's, inside of our hypervisor, definitely, then we have that problem. So for the most part, we can avoid that question. Some tricky bits, just to make it kind of fun and difficult to do. We actually de-virtualize if we like. So if the user says, hey, I don't want to use Jinx anymore, turn it off, we actually get out from underneath the operating system, which is kind of fun. Just really as a debugging tool, but we actually deploy it in the field when we crash, which does happen. Currently, we're in alpha stage. We actually detect the fact that we crash, and we automatically de-virtualize ourselves and get out from underneath the operating system. This is a good way to avoid a blue screen to death. Kind of unfortunate, but Intel and AMD refused to agree when they did hardware virtualization support. And so they both kind of are pretty bad, and they're both pretty different. So we had to deal with that problem. Also, it's not an area of designing, I mean, certainly as Microsoft knows with writing any operating system, it's not a type of application that's forgiving of any error. So the slightest error here, and you've ended the game and you have a crash. And then, of course, in answer to your question, yeah, we do have a little bit of the PC device zoo that we have to manage, and that's fun. All right, so that's one piece of technology that goes into Jinx. The next piece of technology is deterministic execution, and this came out of the University of Washington. So, yeah.
Do you have a paper on the thin hypervisor?
No, but there will be eventually. It's just too cool of a system concept not to write.
Okay, so it's not, the research was done in the PetraVM context.
Yeah, that was completely done inside of PetraVM. So, we will write a paper about it just because I think there really is kind of a neat set of follow-on just systemsy research ideas that can come out of that. This idea of having a cooperative operating system that's slipped in underneath an existing one and helping it do certain things. I think it's a very fun research area to explore. So the next technology is deterministic execution, and I don't have time to go into great depth about it, but there's a research paper at ASPLUS. This came out of the University of Washington with a couple of students, and Louise Seze and myself. And what we mean by deterministic execution is with a sequential program, if you run a sequential program, a single-threaded one, multiple times with the same input, you get the same output. And you're used to this experience. But with a multi-threaded program, this is not the case. If you run a multi-threaded program with the same input, you get different you can conceivably get different outputs every single time. And in retrospect, this seems crazy. But for 60 some odd years, and even now, this is the way multi-core or concurrent programs are expected to behave. And so deterministic multiprocessor execution is a piece of technology that stops that from occurring. So before I go into what I mean by deterministic execution, it's probably better to define kind of what I mean by non-deterministic execution. So here is the same program, but kind of showing three different executions of it. So here you have one execution on the left, here you have one in the middle, and one here on the right. And the difference between these two is precisely how the different threads on processor 0 and processor 1 were interleaved. And so since they differ, eventually the state of memory can be different. And so the actual instructions that are executed can diverge from one execution sequence to another, and hence the outcome can be different. It could just be that even though the execution instructions, the actual instructions that are executed are the same, simply by virtue of how those instructions are scheduled and interleaved on the actual processors, the state of memory can be different. So here, the memory location E could actually be different, even though it's the same exact instructions that were executed between this run of the program and this run of the program. So this is kind of what I mean by the non-deterministic execution, which is even though you have the same program and you've given it the same input, because the threads are interleaved and scheduled at slightly different ways, you can get different output. Okay, so what's the easiest way at which you can solve this? And the easiest way you can solve this is to convert a concurrent program into a sequential program, which is not very exciting, but it is, at least from an academic exercise, it is a trivial way to do it. So you may not want to do this for performance reasons, of course, but here's a way to take a concurrent program and make it deterministic, which is to simply pass a lock back and forth between each processor on every single instruction that you execute. And then as you run it, every single execution will be the same. That's not a lot of fun, so your goal now is to try and recover parallelism. And the way you do that is you make the following insight, which is that it's okay to have non-determinism in the execution as long as the state of memory and who owns various values of memory changes deterministically. So you can kind of take one step removed and say, I don't really care about the exact ordering of instructions in the execution. I only really care about how those instructions communicate. And that communication happens largely through memory. And so if you control that communication so it occurs deterministically, you can recover a lot of the parallelism that happened on the execution side. And so that's the simplest way to kind of understand how to grab back parallelism from an otherwise brain-dead idea. All right, so this is implemented inside the Jinx hypervisor. We are actually able to take a fully running guest operating system and make it deterministic if we like. And the way we do that is, again, by controlling who owns pieces of memory and controlling the exact way at which those pieces of memory change ownership. All right, so yeah.
In the basic idea, the granularity of memory, the way you represented it was was one word. But in your implementation, you think of the memory granularity at the page level.
Exactly.
I see.
Yeah. So we get some aliasing effect from that, which you can think of as a way of, all it does is it ends up reducing parallelism on the processor side. So there is a performance impact, but not a correctness impact from that.
Yes.
All right. So the next piece of technology is really kind of the infrastructure to do simulations and find bugs within those simulations. So what do I mean by simulation? Jinx is able to execute copies of the guest virtual machine and explore those copies and how they execute, looking for ways in which you can try and get to a buggy state in an executable. We don't just do this kind of randomly. We don't just say, hey, let's just take the machine, fork off 10 different copies, run them randomly, and see what happens. It's actually very judicious about how it goes about doing that. And I have a fairly in-depth slide to try and illustrate that. So it's very planned in its process for trying to expose bugs. Once it finds a way or a path through the copy of a virtual machine to find a bug, it replays that path onto the virtual machine that you, the user, is actually experiencing. And of course, all this happens on a real box live as you're sitting there. So you can still actually use your box and play. Some of our customers, write games, and they actually have to test those games interactively. So you can still do that.
So, but I don't.
Yeah.
But what I don't understand is that if I am playing with the box while Jinx is running,
right.
And let's say Jinx made a sequence of judicious choices and crashed. Now I have to localize that crash, right? I have to debug it.
Right.
So there must be a requirement that I play the game in the same way that I played last time, right? In order to go and crash again?
No, we don't guarantee you, largely because of I/O, we don't guarantee that we're going to get you to the exact same crash every time you run Jinx on your software. If your software has, 50 different bugs, you might, each time you run it, you might get 50 different crashes. What we have found actually is that Jinx finds bugs in the proportion that they show up, not do show up, could have shown up in the dynamic execution stream. So it's often the case that if you have 50 different bugs, they're not uniformly distributed in the execution. It's often the case that one of them really dominates the possibility of what might be occurring. And so Jinx will kind of home in and make that bug happen first. Of course, then once you fix that bug, then you get to the second order bug that was hiding underneath that one, and so on and so forth. So we don't give you a guarantee that every time you run a program, you get the same exact bug. We simply, all we're really doing is we're amplifying the chance that any bug will manifest itself.
So, but I want to push on that a little bit.
Yes.
So is I/O the only thing to blame for it? Supposing I gave you a program that doesn't do any I/O.
No, absolutely not. Because there's a little bit of random chance underneath the hood of what Jinx is doing. Okay. So it's not just that. But I mean, you could imagine that we decide to take those random choices away, and then probably, I think you could say it's just I/O that's doing that.
Or record them.
Yeah, or record them. Yeah, but it's really hard to record I/O
right.
on a whole machine scale. But from a theoretical sense, you could imagine that. Yeah.
Previous slide.
Yeah.
So the deterministic memory access execution.
Yeah.
So what you basically do, every memory page is owned by one thread.
Correct.
And when another thread tries to access it, you get memory violation, and then you can remember whatever.
You think of it as if you were doing this in hardware, and the patent that we have on this covers a hardware implementation of it. You would piggyback this on top of the states of a cache, because you have, this is essentially exclusive, this is shared, all right? We're doing it in software, but that's, same thing, basically. We're just emulating that. And so pages are either owned exclusive by a single piece of single processor, or they're shared among all processors. Yeah.
What about user-level threads?
What about what?
User-level threads?
From the perspective of where we are right now, we don't actually have insight to a user-level thread switch. So we work at the level of a processor, and so we look at how communication occurs between one processor and another.
Not a single memory.
Right. So one of our future projects is to kind of tap into the Windows Fibers infrastructure and support kind of debugging across user-level threads. Yeah.
I like fibers. You're actually where you want to go, but that's okay.
Whatever superseded fibers. I mean, there's some new buzzword I'll have to learn.
So you don't provide deterministic execution because you don't have a way to determinize the time in which the I/O occurs and what I/O level.
Yeah, now you're getting into kind of a broad academic question that there was this whole conference across the lake, which is what does it mean to have sort of deterministic languages or deterministic machines going forward? And that's a very difficult kind of question to answer. What we do is we use determinism for one very specific technology. We use it to be able to deterministically replay an execution from a simulation onto reality. It's just a very constrained use of deterministic technology. There is this broader academic question, which I don't think anyone has really answered, which is what does it mean to have a deterministic box, and could that help you in some way?
So, given that you don't have a deterministic replay in that big sense, so why is this useful to have a deterministic execution of just threaded things?
The main purpose it's useful for us is that we're taking a simulation and then we're deciding, hey, this is a great simulation. Let's replay it onto reality. There's only two ways I know to do that efficiently, or there's only two ways I know how to do that. One is to keep a log of that simulation. So every change that simulation does to memory, or every single thing that simulation does, you store it away in a log so you can very carefully replay it. Or you do what we do, which is deterministic execution, which says if we just give it the very precise initial state and an algorithm for how to make deterministic forward progress, it will achieve the same output at the end. So we do it really as a way to mentally compress a log that you would use to replay a simulation.
Oh, that's where you're simulating, and so you can simulate parts of the execution that does not have any I/O.
Or you provide a synthetic I/O device that behaves deterministically, and we have some of those too. There was a question? No? Okay, great. Okay. So just some definitions. When I say simulation, what I mean is a copy of the guest virtual machine, and that copy is running deterministically, but also according to a plan. So we can kind of skew the assignment of resources very carefully to try and steer execution in a given way. As I mentioned earlier, we enter simulation basically from random sampling. We end simulations when we run out of time, or when those simulations actually talk to I/O that we do not synthesize. And then we pick simulations that have bugs, and those are the ones we actually replay onto reality. So here's a kind of cartoon example of what's going on, which is initially Jinx is entirely out of the way, except that it has virtualized the guest. Then we sample and we decide, hey, let's enter a simulation round, and we're going to then explore from that point forward. We do what we call an exploratory simulation. And what this is we run, and we're looking for shared memory communication between these processors. Then once we have done that, we refine that simulation, and we look for how that memory communication could be different going forward in time. So we're really looking at several different simultaneous ways in which the machine could make forward progress. And then ideally, we find one that we think has a crash in it. And finding a crash is not always easy to define what a crash is. But let's assume that we found one with a crash. that's still a simulation. That's not reality. We then go back and we take the root virtual machine that the user is experiencing, and we deterministically replay that onto the root virtual machine so that the user can experience that crash. And then we get completely out of the way and let the box go forward.
So I don't understand, why do you call it a simulation? What is the distinction in your mind between simulation and reality?
One of them is working on a copy of the guest virtual machine that the user is experiencing. That's kind of the simulation. One of them is actually running on the one that the user is really experiencing. So when we're exploring these tens of different virtual machines at once, we really don't want the user to have to, it just wouldn't work. The user we can't manipulate real state. We're really taking copies, clones we call them, of those virtual machines and doing the exploration on those clones.
I see.
So I imagine the clones aren't literally a complete copy of memory. Like if I have an OS that has 4 gigabytes allocated, I don't need an 8 gigabyte machine for me to make a copy. You're just playing games with page tables. And,
you just do copy on write.
yeah.
And it is for that replay that you need the DMP technology.
Exactly.
Because the same algorithm runs on the copy that runs on the original thing.
Right on. Yeah, the same algorithm that got us to this, the same algorithm of page assignments that got us to that particular crash is ran on the root VM to get us to that crash in reality.
Okay.
Yeah, exactly.
So your definition of a bug is a crash?
Well, that's a good question. What is a bug is, we have a scoring mechanism of things that could be bugs. Some things are very easy to say they're bugs. They're asserts. Some things, or they're dereferencing a null pointer. Some things are kind of probabilistically bugs. Like they're an access to memory that isn't in the guest page table. Maybe it's a bug. Maybe it's just on disk. We don't know. But we score it slightly higher than we score other simulations, and we play those.
Right, but you have to be careful at the VM level, right? If the application itself is catching the null pointer dereference and recovering from it, and it's not a bug.
Oh, and that definitely happens. One of the things that Jinx does is applications that do have try-catch blocks and have these exceptional conditions, we end up really cranking on those and throwing out lots of exceptions. So yeah, most definitely, defining what a bug is a tricky business.
How do you, at that level, how do you figure out that a particular null pointer exception was caught?
Oh yeah, we just if we see a null pointer, we say, great, let's throw it in the application and see what happens. But if they're using that for some semantically useful purpose, well, first of all, I think that's crazy software engineering if they're doing that. But we do end up making that much more likely to happen. And this does happen. Like for some reason, the start menu in Windows Vista throws out tons of N3 exceptions. Why? I don't know. But we make those happen all the time. It doesn't crash. It catches them. It does something fun with them. I don't know what. All right. So we obviously, we're pretty smart about how we run. I mentioned we don't just sort of run randomly and try and find bugs looking in the dark. We're really trying to find bugs in a more intelligent way. So what we do is we run this initial exploratory simulation, and we analyze it, and we look at the communication among the threads. And what we see is that processor 0 has talked to pages 1, 2, and 3, and processor 1 to 3, 1, and 3 and 1. So this might imply that, first of all, there's 5 instructions that might be communicating and on 2 pages. So we actually refine that. We run another simulation to look at what are the actual words that are being used to communicate on those pages. And then when we do that, we find that, in fact, there are only 2 instructions and there are only 2 words of shared memory in this simulation. And then this tells us how we could take this initial sequence of execution and generate 2 completely different executions that might lead to different outcomes. And that's what I'll show next, which is we could take this initial execution and reschedule it very carefully so that these 3 instructions completely precede the follow-on instructions here. That's one what we call plan. Or we could reschedule it such that these 3 instructions completely precede these 3 instructions. And hopefully you can convince yourself that these may lead to different outcomes in the actual execution. So these are what we call plans. And what we're constantly doing under the hood is we're looking at execution. We're analyzing the memory communication. And we're trying to figure out what are the different ways at which we can perturb that execution and then create a new sequence that would lead to a different outcome. And you can't just, I've kind of shown this cartoon style, but we don't just sort of pick the addresses at random from an execution. There's a lot of kind of intelligence that goes into figuring out what is a good plan for exploration. All right, some subtleties. How do you execute a plan? I think this has probably been answered by the questions, which is great. The executions are always using the deterministic algorithms. We essentially control the algorithm to very carefully orchestrate what resources are assigned, and that orchestrates what forward progress occurs on the actual processors. Do all plans actually complete? Yeah.
So this is actually more than what was explained in the DMP paper.
Oh, it's totally different.
Because here, the DMP paper says, okay, I'm going to pick one particular deterministic scheduling strategy, and you don't have any control over it.
Yeah,
but you actually want to give that as an input to the system too, right?
Yeah. There's a whole bit of follow-on IP that's been generated at Petra from that initial idea. Yeah, most definitely. So one question you might ponder is, do all our plans actually complete? There's ways, first of all, there's naive ways to generate plans that just, trivially will not complete. But you can generate a plan that should complete, and then you run it on a real box, and it does not. And the main reason it does not is I/O. You have some memory devices, you have some I/O devices that will change the state of memory under the hood from you. And you have to be able to deal with that. So we call these a desynchronization. It doesn't affect your box. It doesn't blue screen. It just affects the performance of finding bugs. What about I/O? Essentially, we classify I/O into either a simulation ending event or an event that we know how to fake. So we have a set of synthetic devices. We've talked about that a lot. And then all of this has to be really fast. So if this is not fast enough, the user experiences what we kind of call GUI lag, which is their mouse gets really jerky because that's the time at which we're freezing their box and looking for bugs. And that's kind of annoying. So this has to be really fast. All right. This is the last part. And this is what we think is kind of taking debugging of concurrent programs to really a next level of understanding why bugs have happened. And this is kind of a unique feature of Jinx and something that we can do because we're running these simulations of reality. If you had a bug, suppose you found this null pointer dereference in simulation, and then, or just outside of simulation, you just ran this without Jinx. Normally what would happen is this would trigger into the operating system, and then this other thread that was running that actually wrote the null pointer into location 1003, it would just keep on running. And so eventually the operating system would call up the debugger would stop all the threads, but where they stopped is completely random. And so you often have this problem when you have a corrupted memory state on one thread, a very difficult time in reasoning about what other thread and what location in that thread wrote that corrupt memory location. So if we find that bug in simulation, what we're able to do is do some detailed analysis to understand, hey, this was the location on the other thread in time at which that location was written, and we can freeze it right there. So instead of stopping the thread somewhat randomly, we drop all the threads we drop the thread that crashed into its crash point, and we drop the other threads into their kind of meaningful point in relation to that crash. And this, we hope, will make it much easier to debug concurrent programs. Just let you in a little bit of humor. Internally, we wanted to call this thing stop short, but if you know that reference, you'll kind of understand why the marketing department overruled that. So some subtleties. How do you choose the correct place to stop threads? Well, that's a tricky business, right? There are several different places at which you can choose to stop threads. And we go through this analysis to try and give you what we think is the best and most meaningful point at which to stop them. But that's pretty tricky business. We do have this issue, which is what if the cause and effect between the execution that created the bug and the effect, the actual catch of the bug, is very long in time. And in our case, what happens if it's outside of a single round of simulation? And in that case, SmartStop does not work. we're not able to actually understand because it's way back in the machine time where we can't, it's already been committed. And then when should you use SmartStop? So going back to the earlier question about what's an error, you do not want to trap yourself in a debugger on plausible errors. We would like to go into debugger directly when we know for sure that it's an actual error. So we do have an issue of defining that. All right, some data. I don't have any graphs. I realize as an academic that's bad of me, but internally we have a lot of benchmarks that we use. So we actually, our QA is not just, does it crash and does it work? Our QA is, what's the bugs found per second? So we're constantly taking a bunch of benchmarks that we have and trying to drive down the repo rate so we can find bugs faster and faster and faster. We can definitely take large code bases like MySQL. We can nuke those pretty quickly if we run them under Jinx. I can tell you that Visual Studio has some issues. And kind of our initial feedback from customers on our alpha product is definitely pretty positive. Our demo, so let's hope we don't have demo-itis here. Here's Jinx. Maybe.
You just crashed Visual Studio.
No, that's great. So this is a pretty obvious bug, really. So this is something where you should have had just one critical section. This is a work queue. You have a thread stuffing stuff into a queue, and another thread pulling stuff off, and you need to lock some control structures of that. And the programmer, or really us, we've introduced for this demonstration a pretty obvious bug where you should not have unlocked it and then relocked it. So you can run this without Jinx. Anyway, you can run this without Jinx, and it'll run for quite some time and not actually crash. So the chance of that unlock-lock sequence actually breaking and splitting in just the right bad point is pretty rare.
So what is the adversary thread doing? You don't show the code.
I'll show you later, but it's stuffing stuff into the queue. Okay. And then if we, here it's still running. If we turn on Jinx, it should, if our demo doesn't going to have. Well, there we go. OK, so usually it's a little bit faster, but Jinx has basically made that happen for us in a time that's much quicker than reality. So
it's violating the linked list invariant, right? That's what the assertion is. The unit arrow, next arrow, prev equals unit.
Yeah. So I'll show you the rest of the code. This is a piece of sample code that we use. Yeah, I will. So, did you want to see the rest of the code, or do you want to?
No, it's
fine. I understand. Yeah. So we give you some features of it. Right now, what we do is we ask you to register your applications. But if you don't want to do that, and a lot of our customers, at least for their trial, they don't want to go through the process of recompiling. You can do something like, hey, just look at the whole system, And then when we do that, you can go over to status, and you see that we're doing these simulations. Here, this is simulations conducted. This is simulations that have sharing. And then if you have, since we're doing full system simulation, you've got to be a little careful. Like, as I mentioned, the grid controls over here, they have some problems. If you click down there often enough, you'll crash them. But you can also go through, we have different strategies. There's different AIs you can use to try and find bugs, different times at which you can do. This kind of affects how often you sample execution. So if you want to go in pretty rarely, which for games or interactive applications you might want to do, or you can kind of crank it up and say, hey, just I run a unit test, just run as hard as you can, and I'll walk away from the box. What else can you do? Our new UI, which will come out for beta, will kind of integrate with Visual Studio, and you can dock it in Visual Studio 2010, and its preference panes all kind of integrate, so that'll be fun. That's the demo. So
Can we look at the assert real quick?
yeah.
Just to see. So does this use the Jinx assert or the regular?
I think we've converted these to Jinx asserts, but what Jinx asserts do,
Yeah, what's the difference?
the difference is that Jinx assert is a wrapper for a normal assert. And what it does is it first communicates to the hypervisor and says, this is an assert. And then it returns back normally, and you run the normal assert path. And what that really does is that we have the scoring mechanism for plausible bugs to actual bugs. That's like a red flag in the sand, bug. We go home in on that. Yeah.
Well, it's just a way so that Jinx doesn't drop it on the floor
Exactly.
because of its whatever heuristic it has for IC.
Exactly.
Does that also enable the smart stop stuff? Like because it's the big red flag, it's like, okay, this is one where I should do the smart stop.
Exactly.
And breakpoints and other
Yeah.
like that all control smart stuff.
Yeah. Okay. Yeah, Burton.
So I understand why you don't keep the entire path of checkpoints. I think, at least, I understand. You have no guarantee of determinism between them, really. You don't know whether you can get back to the same checkpoint you know, if A leads to B this run, and I go back to A and start up again.
I kind of think about it as a sphere of things that we control.
Yeah.
And once communication leaves that sphere,
Right.
we kind of have to commit and get out of the way. And so, if we have synthetic I/O devices, which we have some of,
Yep.
they're in our world. But if we have others, like we don't have a synthetic hard disk, or we don't have a synthetic network internet. You know, once the packet's left, this is the same problem as transactions. Like once the packet's left the network card, it's left. And so we don't have a way of rolling that back. Yeah.
I'm just wondering, you know, whether there's some halfway houses between where you are with this product and where you might want to take it.
Most definitely. There's some future products that would extend that sphere out.
Yeah,
All right, some related work. A lot of the related work, of course, is being done by people in this room. And then there's some other products out there. I think the big difference, or big differentiator between Jinx and these other efforts is that, first of all, Jinx is a hypervisor, so it's working at the complete machine level. And then we're taking this kind of simulation-based approach. So we can run from that snapshot of a machine over and over and over again, trying to refine that to create a bug. That's, I think, the two key differentiators in there. But these are all great efforts, and it's great to have them out there. All right, so just to conclude, definitely ran longer than I wanted, but that's fabulous. You know, Petra VM has implemented a thin hypervisor, and I think it's probably the first commercial product based around the thin hypervisor concept. There's other things out there like rootkits based on thin hypervisors, but I think we're the first product, actually. It's able to execute an OS deterministically. It's also able to execute it speculatively, so we can take copies of that guest operating system, run them, discard them, commit them to memory if we like, et cetera, et cetera. And there's some intelligence under the hood that we can use to steer those copies as we desire. Is our first product, Jinx. Jinx is going to come out in beta testing in late January, early February, and I think it would be fabulous if Microsoft would like to be part of the beta program. I would love to see that happen. It's able to find bugs. There's going to be a somewhat public beta. And the future is that we have this kind of really nifty platform that we can use and steer it towards different products and solving different problems in the multicore space. So thanks for coming, and thanks for those of you that saw it online. So, questions? No? Thanks.
I think they probably already asked you all.
Yeah, I think that's how a talk should go, so thanks.
What's your business model?
What?
What's your business model?
Well, we want to make multi-core programming for the masses possible.
So you're going to sell my bugs or sell my...
Ask me later and you can join our company. All right, thanks.